All right, class, we're going to get started. Okay, so today we have three things to get through. The end of lecture 10. So we talked about propagation of uncertainty when we have a nonlinear function. And so where we left off was we looked at the way that we're going to propagate uncertainty when we have a nonlinear function at the end of last lecture. So just pick up from there and we'll look at application of this to an example, right? So again, this is an extension of what we did for linear combination of variables, but now we have a nonlinear combination of variables. We'll be able to propagate uncertainty. Second thing is lecture 11, which will be the basically how we can use what we've learned so far for hypothesis testing, but how we can apply that to look at comparing two different samples. So this would be like paired hypothesis testing or two sample hypothesis testing. And we'll look at two different ways that we can do that. Third thing I want to do at the end is, if we have time, is look at the quiz. So quiz 3. So you should have seen our return grades. They should be available on Canvas. I return them as well on Gradescope. And so I just want to talk through quiz 3, and that will likely be after the lectures, probably after 4 o'clock or so. So did I miss anything? Anything else we need to cover today? Okay. Any questions from last time or from previously? Okay, so next week obviously is fall break. So we've just about made it to fall break, at least in this class. I know you still have the rest of the week in your other classes. This will be our last class before fall break. There will be a homework. I will post it tonight, but it won't be due until after fall break. So I'm not going to have something due for you during fall break. All right. But you'll just have extra time to work on this one. Any questions? All right. So last time we discussed the formula or how we can propagate uncertainties if we have a nonlinear function. So just as a reminder, again, in lecture 1, we talked about lecture 1 covered on quiz 1 and quiz 2. We talked about propagation of uncertainties when we have a linear combination of variables, right? So we had an example where we were looking at a process time that is, right, we have a total process time that's composed of, I don't know, it was a coding step and a rinse step. And we knew the uncertainty in the duration of the coding step. We knew the uncertainty in the duration of the rinse step. But let's say we want to figure out what is the uncertainty that we expect to see, the variation in total process, or in the total process time. What is the variation in total process time that we expect to see when we combine those things together? We saw this on quiz 2. We're looking at like lengths of wire being wrapped around different shapes, and we used the same, it was a linear combination of multiple different random variables, and we saw that we could combine that. We saw how to combine that in lecture 1. So what we have now, so that equation 10, we can think of as a generalization of that idea from lecture 1, but for a nonlinear function. And so as an example, what we're going to go through at the beginning of this class today is, let's say we have we're measuring the velocity u of an airstream in a duct, and we know that that velocity u is related to other parameters like delta P, the pressure difference that we measure, some temperature and some ambient pressure, as well as universal gas constant. So we have u as a function of, we'll say, 3 variables. We'll treat r as a constant, right? So we have 3 variables, delta P, ambient temperature, and ambient pressure. But it's now a nonlinear function of those 3 things. And so if we know what we're going to do here is given uncertainties in ambient pressure, ambient temperature, and the measured delta P, we're going to propagate those uncertainties through using this expression to figure out what is the expected uncertainty in this variable u. Does that general procedure make sense? We haven't shown how to do it yet, but the way we're going to do it is by application of that equation 10. Okay. So what we're given here is that we have a delta P of 8 plus or minus 0.1 inches of water. Right? So we're measuring pressure in terms of inches of a column of water. And it's stated that that plus or minus 0.1 is a 95% confidence interval. The ambient temperature, 527 plus or minus 0.2 Rankine, again, 95% confidence interval. And the ambient pressure, we're told, is 14.7 plus or minus 0.3 psi-A. So that's also a 95% confidence interval. And so what we said last time, just as a review, when we're propagating uncertainties, we can use the expression for propagating uncertainties was shown above in equation 10 to propagate standard deviations, or we can also use it to propagate our 95% confidence intervals that we've calculated using t-distribution or normal distribution if our sample size is large enough. So here we're given 95% confidence intervals on those variables, and now we're going to propagate it through the expression. So when we use this expression up here, so equation 10 shows the uncertainty in our final function value, that SF, we're going to say is the uncertainty in that final function value. We've expressed it, though, in a form where we're normalizing that uncertainty, that SF, by the value of the function itself. So SF, so we'd say this is a fractional or it's a normalized uncertainty. So it's like a percent variation in that value. And we can express that so if we cast everything in terms of the normalized values, so the values of the expression relative to, so the value of the uncertainty relative to what its mean value is. So it's like SF, we could say SF over mu F would be another way of writing that. The right-hand side of equation 10 is now our propagation of uncertainty formula that's in terms of the relative values or the fractional values of uncertainties. So we'll see here, for example, it's some coefficient. What we end up with is some coefficient that we're going to find through the functional form, like F as a function of all of our different variables, multiplied by the actual fractional uncertainty in each variable. And basically what we're tasked with in trying to propagate uncertainties through from this formula is first we have to find this first coefficient piece by doing the calculus, by plugging in the what our function is and taking partial derivatives of that function. So we're going to find what this coefficient is, and then multiply that by the fractional uncertainty in our variable. Square that. Do it for the next variable. Square that. Add all of those up, and then what we end up with is the fractional uncertainty squared in our final functional form. Does that general idea make sense? Okay. So we think this is like trying to find, again, we're just going to basically be trying to find the coefficient that we're multiplying our fractional uncertainty by. So an advantage of doing this is if we go down here, in this formula and in this example, we're given all kinds of crazy units, right? Like we have inches of water, we have PSI, right? Pounds per square inch. We have Rankine for temperature. We have all these kinds of crazy kinds of units. But if we use this expression 10 or equation 10, everything here is non-dimensional. Nothing here has units. All those units will drop out of this expression. So we'll end up with we'll end up with an uncertainty relative to whatever the functional value is, and all of our uncertainties of the inputs will be relative to what their value is. So, for example, we would take to find SI over mu I for this delta P, it would be the uncertainty, the 0.1 divided by the value 8, right, would give us the fractional uncertainty in that value for delta P. Does that make sense? So it's this equation 10 is giving us the relative uncertainty relative to the mean, instead of an absolute uncertainty. So when we take this expression, if we do the, and that general procedure is kind of explained up here in equation 11. So from equation 10, again, we've kind of reduced this problem to, first of all, computing the relative uncertainties of each one of our variables. That'd be like the SI over mu I for each one of those variables. And for each variable, estimating this first parameter here, which I'm calling the sensitivity. And we find this by looking at the analytical formula for that we're given, right? The functional form that we're given. Okay. You'll see this on your homework to maybe make this concrete with a practice example. So when we, if we look at equation 12, if we evaluate, so again, that SI over mu I, we could write this out for example, for delta P, it's going to be whatever the uncertainty in delta P is, again, that 0.1 inches, divided by the actual value or the mean value of delta P, which is 8, right? So that's how we'd find this S delta P over delta P. And if you go through and do the calculus, take the partial derivative of this and multiply it by delta P over U, right? So to come up here, it'd be delta P over U times the partial of U with respect to delta P. What you end up with is 1/2. So this coefficient here becomes 1/2. And so we're going to take that quantity squared. We'll go through the same procedure for the ambient pressure, PA. Again, SPA is our uncertainty in that ambient pressure. It's 0.3 PSI. Normalized by PA, it's 14.7. And then this 1/2 comes from evaluating this thing here. So it'd be PA over U times du dPA, right? Partial of U with respect to ambient pressure. And again, that just resolves to 1/2, right? So we take that quantity squared and we add it to, we do the same procedure for ambient temperature. We end up with the same actually coefficient in this case. And then the square root of that entire expression, right after we add up all of those parameters together, gives us the relative uncertainty in the velocity, right? And what are the dimensions of this thing? So what are the dimensions of SU over U? Yeah, go ahead. Nothing. There are no dimensions of this SU over U, right? Because our uncertainty for the velocity would be in terms of meters per second or whatever we want, right? And so then we're dividing that by velocity, which would be also in, let's say, meters per second or something. So meters per second over meters per second gives us something with no dimensions, right? No units. Okay, so that's the advantage of using this fractional approach. I had a question right here. Yep, and then we'll go. No, it really depends on the expression. In this case, they happen to be the same, but they're not always going to be the same. Okay, yeah, that's a very important thing. So these coefficients are not the same, are not always going to be the same for all the different variables. Okay, so yeah, these will not always be the same. Yeah. Mm-hmm. And then when you divide by the functional form of U, then it should drop out, and you end up with just that 1/2. So you have to look at this. You have to do this whole thing, right? So it's delta P over U. The way to interpret this for this first coefficient, it's delta P over U times the partial of U with respect to delta P. Okay, and that entire expression is what evaluates to this 1/2. That's what I'm calling here the sensitivity. Okay. Yep. Good question. Other questions? Okay. All right. So then once we have the sensitivities and we have these fractional uncertainties from, right, the sensitivities are what we find from the functional form, and we have the uncertainties, the relative uncertainties, then we can combine them together. and end up with our final estimate. And so what we end up here is with a fractional uncertainty of about 1.2%. Yeah, we end up with a fractional uncertainty of about 1.2%. This example goes a little bit further and says that the greatest reduction will come from improving the measurement of PA, and that's just based on computing the relative uncertainties of all of the different parameters, multiplying by those sensitivities and seeing which one is largest. So whichever one is largest is the one that has the most contribution to the ultimate uncertainty in your result. Okay, so that's what this second piece is here. All right, and that's you can see that computed. So the Python code to compute that is up here, but we can see that the largest one was the term relating to the ambient pressure, and so that's where that came from. Just a few other notes. This gets into estimating uncertainties. So it may be the case, let's say you're given the task of estimating the uncertainty in the velocity from this pitot tube or something. So you have a formula for U as a function of, as a function of delta P, ambient pressure, and ambient temperature. And let's say you're given a confidence interval, 95% confidence interval on the measurement of delta P or something, right? Like because you have good data set to actually estimate that. You may not always have a good data set to use to estimate the uncertainty in all of the variables that go into a process. Now, that doesn't mean that you can't say anything about uncertainty. You can still say something about how uncertain those other things are. So, so you cannot always calculate uncertainty from a set of data. So sometimes you need to rely on judgment and experience, right? So that might be just listening to the person who actually runs the process and hearing what they have to say about what the uncertainty and temperature is. And you can use that as your uncertainty that you propagate through that expression. Okay. It's better than nothing, right? And it actually, in some cases, may be better than what you'd get by, I don't know, running a whole set of experiments yourself. But you can also look at just the scale or look at the way the measurement is being performed. So a lot of times you may have, let's say you have an instrument with an analog scale, right? You have ticks on a thermometer or something that's being used to read out the ambient temperature. So just as a rule of thumb, half of the smallest scale division is a reasonable estimate of the uncertainty, right? So you have a thermometer, the operator there is sitting and reading temperature off the thermometer. You definitely cannot estimate that temperature to better than the smallest scale that's on the thermometer, the smallest set of ticks that are on the thermometer. So half the smallest scale division would at least get you started on estimating the uncertainty, right? Not as good as having a set of data from which to calculate uncertainty. Not as good as having, talking to someone who's experienced with it and can tell you what the actual range of temperatures is, but it's better than nothing, right? It's at least a starting point. And same thing for digital scales, about half the value of an increment for the least significant digit could work. Or oftentimes for an instrument, you may be able to look up what the measurement uncertainty is for that instrument. So that'd be another source of this, would be manufacturer data sheets. And again, if I were trying to have this pitot tube, right? That is going to make measurements of velocity. If let's say I have data to estimate the uncertainty in delta P, maybe I just have manufacturer data sheet that's going to tell me what kind of uncertainty I have in my measurement of ambient temperature, and a different manufacturer data sheet. Or maybe I have no manufacturer data sheet for ambient pressure, but I just have, I know what the smallest least significant digit is in that measurement, in that readout. I can use those things to help estimate at least what the uncertainty is. Does that make sense? So this is kind of real world. You don't always have a data set. You don't always have a 95% confidence interval, right? Or even the data from which to compute a 95% confidence interval. but you may still be asked to make an estimate of uncertainty. And so this is just one way of going around that. Okay. Okay, one more note, which is related to propagation of uncertainties, and is more just like it's here as a more practical consideration. So let's say we have results for some process that came from multiple different groups or laboratories or measurement procedures. It may often be the case that the uncertainties in those results vary based on where the data came from, right? So maybe you have a set of samples and you sent one set out, historically you sent one set out to a certain laboratory that was really, really good. And now that laboratory shut down and you have some additional data and you sent it out to another laboratory that's not nearly as good. And you want to now combine those values, the values from these multiple different groups together and estimate the uncertainty, the resulting uncertainty in this much larger data set. One approach to combining that is to basically estimate or compute an average of the results that's weighted by the uncertainty in those results. So what you end up doing here, if you apply this formula 16, equation 16, is you end up weighting the results from the more reliable laboratory more heavily than the results from the unreliable laboratory. Does that make sense? A little bit of sense, right? So if we do that, if you follow such a procedure, then you can use this expression in equation 17 to estimate what the overall uncertainty is in that combination of results, or when you've combined the results that way. Okay. So again, getting to real world use case where we don't always have all of our results from one experiment run by one operator, done under a certain set of conditions. So you may sometimes have to combine results from multiple labs or processes. Yeah. A would be the variable that we're trying to measure. A could be our delta P or something, right? In the previous expression. A could be, the process yield, right? So we use process yield. A could be process yield, right? So let's say we have process yield being analyzed by a laboratory. We're sending out a sample to a laboratory measuring process yield. Laboratory A gives us back process yield with an uncertainty of 2%, fractional uncertainty of 2%. And laboratory B gives us results back with an uncertainty of 10%. They don't have instruments that are as good, right? We can still combine them together to get an estimate of what the overall process yield was. And then this tells us what the resulting uncertainty is, okay? Yeah. Or it might be the case, maybe we've been sending it to laboratory A all along, but laboratory A gets better instruments, right? So their results get better, but we still want to use the historical data. This will help us. Yeah. Okay. So we took a little bit of a diversion from hypothesis testing to talk about uncertainties, because again, just to review, a few lectures ago, we discussed how to compute 95% confidence intervals, knowing what the underlying distribution of the data is. We can estimate 95% confidence intervals on measured values of or from data. So in engineering, we are often going to be using those measured values to then estimate something else further down the line. So we can use this propagation of uncertainties idea to propagate not only the mean value, but also the uncertainty. And as an aside, I mentioned that as an engineer, oftentimes communicating uncertainty is just as important as communicating the mean result. And so this can be a very critical part of your work. But now we're going to step back into hypothesis testing. We're going to look at hypothesis testing when we have two samples and we want to compare the mean results of those two samples. But any questions on uncertainty and its propagation before we go there? Okay. And again, you'll see this on your homework. All right, so now we're in lecture notes 11, comparing two conditions. I apologize, I posted this to Canvas just before class was starting. So if you tried to download it earlier today, you wouldn't have seen it on Canvas, but it should be up there now. Are you able to access this on Canvas? Anybody who's looking? Okay. see some nods. Okay, good. And there's also some files that you need for this as well, and they should be there. All right, so it is often the case, right, that we want to make a comparison between two different situations, right? So we have two sets of experiments, and we want to know, are the results the same or not? So that's what we're going to be looking at today. And there are, in general, we're going to look at two different situations when we're trying to make a comparison. The first is when we have what we call a paired or matched comparison. So this is when we're trying to say something about the average results from, let's say, a set of experiments that are under identical conditions, right? We've just changed, let's say, one of the variables, but otherwise everything is identical about those two sets. So that would be a paired or a matched comparison. And then there's the more general case where we're just trying to look at the difference between two means, but we can't necessarily guarantee that everything about the experiments was the same. So we'll start with the first case, and we're going to do this by way of an example. So let's say we have a cab company, right? We're running a taxi cab company. There are two different gasoline suppliers, A and B. And they're supposed to be of the same grade, but we have a suspicion that that they're not actually the same, right? That maybe one of these gasoline is actually giving a slightly better gas mileage than the other. So in this case, we're going to say we're randomly assigned gas A or gas B to the same cab with the same driver. So we have nicely matched sets of experiments on 2 consecutive days. And we have 10 cabs are tested and the data are compiled in that spreadsheet, right? L10 paired cabs. So we'll say we would call this a paired comparison because the 2 fuels are being tested in the same cabs with the same drivers, right? So we should expect that that we can actually make a pairwise comparison. We're saying it's a pair test because we make a pairwise comparison between our results. So we can take the results with gasoline A on one particular day in one particular cab to gasoline B in the same cab, same driver, and so on. And so we end up with pairwise results here, where for each individual cab, we have results of miles per gallon with gas A and miles per gallon with gas B. We've read this in with pandas, and we've used that head function in order to just look at the first 5 rows in the data. In this case, we're just creating a new column then, which is the difference. So in a pairwise comparison, we're often going to be looking at the difference between the paired values. And so we make that column here for the difference between the paired values. And then we're going to we can use the describe function to look at our summary statistics on that column. And here we see that there's a mean of -0.6, right? Meaning that in this case, the gas B had a slightly higher average miles per gallon than gas A. But the question we want to answer, and the reason we're using statistics here, is that meaningful, right? Is that significant? Right? Should we switch to gas supplier B, or do we not have enough evidence to say that gas B is better than gas A? Right, so that's the purpose of this test. And so first thing to do is we need to understand that we can actually use our t distribution or normal distribution. Like what can we actually use to analyze this data? So remember, so we only have a sample size of 10. So it would not satisfy criteria for us to use a normal distribution to make an estimate of uncertainty or 95% confidence intervals or do some kind of a statistical test on the data, right? But in order to use the t distribution to compare or to look at the mean of this set of experiments, we need to know that the underlying distribution of the population should be normally distributed, right? That underlying distribution should be normal. And so here we're plotting a histogram of the data for the difference. So this is histogram showing frequency versus difference between the 2 means. And I don't know, kind of sort of looks like a normal distribution in that it's higher in the middle and has tails on either side. We can't rigorously show that this is a normal distribution, but it's at least, I don't know, we'll say it's normal enough that we're going to proceed using t-test in order to analyze this data. Okay. Yeah, so it says here, the histogram shows that the distribution of differences is roughly, and we'll say very roughly, normal. And so we'll take this as justification to use the t distribution for the hypothesis test. And what we're going to do is we're going to look at the, so when we have these paired measurements, so we can make a pairwise comparison, right? So for the same cab, we have measurements for gas A and gas B, right? And that's the sense in which these measurements are paired. Then we're now going to be comparing, we're now going to do a t-test where we're comparing we're comparing the difference values, the difference between the pairs and our statistics on the pairwise differences. We're going to use a t-test on those pairwise differences. So we're going to set up a hypothesis test here. Our null hypothesis is that there's no difference in mileage between gas A and gas B. Right. So at the outset, we didn't know if gas A or gas B is better. We just want to know if they're different. So our null hypothesis here is not gas A is better than gas B or gas B is better than gas A. Our null hypothesis is that there's no difference in mileage between the two. Right. So this is the thing that we're testing against. Our alternate hypothesis is that there is, in fact, a difference between the two. Okay, so it's a little different than what we set up last time, right? But here, our null hypothesis is that there's no difference between the two. Yeah.
So how much you need to
Yeah, I guess it comes back to the claim that you're trying to evaluate, right? So in this case, the claim that we're evaluating, the claim is that gas A and gas B are the same. And so our null hypothesis is that they're the same, right? If the claim were that gas B was better than gas A, right, then I would set up a hypothesis test to test that claim. Does that make sense? And what the biggest difference that we'll see is that if you remember last lecture, I showed my sort of hastily drawn sketches of the distributions, the underlying distributions. And when we're making a claim of one thing greater or less than the other, we're out on one tail or the other of the distribution. And we're going to say that if we're in that tail, if we're far enough in that tail, then we reject the claim, right? And we end up with accepting the alternative hypothesis. Or we reject the null hypothesis, rather, and we end up accepting the alternative hypothesis. In this case, when the null hypothesis doesn't state one way or the other, it's greater or less than, then we're actually going to, if we're in either tail, then we're going to end up rejecting the null hypothesis.
And then is the area of the two tails in the case where it's not equal the same as the area of one tail?
Yeah, so that's an important, yes, that's an important note. So the question is the area in the tail the same as it would be if we were looking at a claim in one direction or the other? And the answer is, like, for a chosen significance level, remember we looked at significance level of 0.05, alpha 0.05. Then if we had a one-sided t-test, is what we would call that, where we're looking at the claim, we're trying to evaluate this claim of, is it greater or less than a certain value, right? Is the mean greater or less than a certain value? We chose our t-value for that we're evaluating against, this t alpha, was chosen such that the area in the tail was alpha % of the overall distribution, right? So if alpha is 0.05, then we choose that our t-value that we're testing against, our t alpha, is the critical value of the t distribution, where we have 5% of the area under the t distribution out in that one single tail. So an important difference here, as you noted, is that we have a two-sided, we call this a two-sided t-test, right? Because again, if our answer lies in either tail, we're going to reject the null hypothesis. But now for a two-sided t-test, let's say at alpha of 0.05, right, or a significance of 0.05, we're going to choose our t-values such that the total area in both tails sums to 5%. So in practice, that means that we're looking at a t-value according to alpha over 2 on one tail, or a t-value of alpha over 2 in the other tail. Does that make sense?
Yeah.
So yep.
That it's easier to prove if the not equal test versus a greater than or less than test when you always, in that case, want to do a not test for your alternative hypothesis.
Yeah. So the question is, since this seems easier to prove, why wouldn't you just always do this or the other way around? I guess that gets into the ethics of statistics again and setting up your problem correctly from the outset. So clearly describe what claim it is you're trying to evaluate, and then set up your test appropriately for the claim you're trying to evaluate. And yeah, there's a whole book, How to Lie with Statistics, and this would be one way of effectively trying to lie with statistics. P-hacking, something we talked about last time. It's not really core material for the course, but ending the experiment when you get a result that you want, instead of ending the result after the number of trials that you said you were going to do from the outset. That's another way of kind of lying with stats. But yeah, so I'm going to watch out for you, I guess, in the future when you're using things from stats. You're picking out all the ways that we can use stats to lie about it. But yeah, these are important, definitely important considerations. Yeah. So yeah, you want to set this up to evaluate a specific claim. Okay. And that's not a formal accusation, by the way. All right, so in this case, we have a small sample, right? Our sample is 10. So our number of degrees of freedom, in this case, well, so our sample size is 10. So we have we definitely have to use the t-statistic, not the normal distribution, right? And that's because again, remember the t-distribution basically becomes the normal distribution when our number of degrees of freedom, or when our sample size approaches about 30 or so. The t-distribution and normal distribution are about the same. And so for simplicity, we just use the normal distribution. You could use t if you wanted to, but you would get the same result. And so now we're going to compute the small sample t-statistic for our measured values. So this is going to be the sample mean minus the mean that we're testing against, the null hypothesis, over the standard error of that value. In this case, the mean that we're testing against in the null hypothesis is just 0, right? So we're testing against the null hypothesis that the two means are equal. So that means that the difference between the means is 0. And so this is just the sample mean minus 0 over the standard error. And so we end up with, from our measured values, we have a t-statistic of minus 3.12. And so now we look at, we're going to compute our degrees of freedom. So in this case, we had a pairwise, we're making a pairwise comparison between these two sets of experiments. So we're going to take the number of, essentially the number of rows in our table, right? Or the total number of pairs, right? That's, so the total number of differences that we have, which in this case is 10, minus 1 is going to give us our degrees of freedom. This is the same as it has been so far, so nothing has changed yet, but I'll tell you, I'm pointing this out to you because it will change in the next example that we're going to look at, okay? So when we have a pairwise comparison, our degrees of freedom is the number of pairs that we have, right, minus 1. So remember, we sent cabs out 20 times total, right? So because we sent each cab out twice, once with gas A, once with gas B. But we did that in 10 pairs. And so we ended up with 10 estimates of the difference in miles per gallon. So this is the number of pairs minus 1 is the degrees of freedom. That makes sense? This small thing to trip up on, but that may trip you up. So just so that's something to keep in mind. So from that, using that degrees of freedom and the t-distribution, we can then compute. So in this case, we're using our NumPy functions to compute the probability that we have a difference between the two means that is at least as large as what we observed, that 3.12. And note here, we're multiplying by 2 because we're trying to evaluate that, like, what is the probability of seeing a mean that is at least as extreme, difference in mean values that's at least as extreme as what we observed. And so this is like, we're looking at, so we're going to take the area in one of our tails, right? And we're going to take the area in both of our tails, right? So the area in both tails of the t-distribution ends up giving us the probability that we would see a result at least as extreme as what we observed. Does that make sense? In either direction. So we multiply that probability by 2, and we end up with an end result that we only expect to see a result as extreme as what we observed about 1.2% of the time. So our p-value is about 0.012, which would mean that at a significance level of 0.05, we've definitely rejected the null hypothesis, right? So we see results that are indicate an extreme enough difference between gas A and gas B that we reject the null hypothesis, and that there is a difference, right? Meaning that we saw a difference between gas A and B that is highly unlikely to be due to chance. Okay. So an alternative way of conducting this hypothesis test. So again, we saw last time that we can conduct a hypothesis test by either looking at our p-value, computing a p-value, and comparing it to our level of significance, our alpha. So in this case, that's what we did. We computed p-value 0.012. We said it's less than our significance of 0.05, and therefore we reject null hypothesis. It's equivalent to also, we could also look, an equivalent way to approach this is to just look at the t-statistic without those p-values. Compute the t-value. In this case, we would see that t-value for alpha over 2, so 0.05 over 2, right, or 0.025, with a number of degrees of freedom of 9, ends up with 2.26. And we can use the same, scroll up here. We can use this same, this table here to say that we're now going to look at, we're now going to compare our t-statistic to the t alpha over 2. And we see that, in fact, our t-value, which was, our t-statistic value was minus 3.1. It is, in fact, less than that minus 2.62. Right? It's less than minus 2.62, and therefore we are going to reject the null hypothesis. Right? Does that make sense? So this is entirely equivalent to doing the p. Entirely equivalent to computing a p-value first. You can do either way. So put another way, by computing the p-value, we are estimating the probability that we saw a result at least as extreme as what we actually observed. And we estimated that probability to be 1.2%. And that was based on how far out to the edge of our t-statistic our observed result was, right? So it told us how extreme our result was relative to seeing no difference in means. But since the way we estimated that was by looking at t-statistic and figuring out where it falls on the t-distribution, we could also, alternatively, we could compute the value of the t-statistic that indicates that we have something that, or have a result that is extreme enough to reject the null hypothesis, and just compare t-statistics instead. And so that's what's summarized in this table here, and that's what's done in the second piece of this question. Okay, any questions on that? Again, we'll get some practice on the homework. So as a final calculation here, we can also, again, use the methods from previous lectures to compute a 95% confidence interval from the t-distribution on what our observed mean was. And so in this case, our t-statistic is based on that alpha over 2. what we end up with is a margin of error based on our results, based on the observed standard error. 0.4 standard error in that t statistic is 0.439. And so therefore we would estimate that the mean is negative 0.6 plus or minus 0.439. Or we could estimate upper and lower bounds on 95% confidence interval, right, as just taking the mean plus or minus what our confidence interval was. Okay, any questions on that? So that was paired. So when we have a paired set of experiments, that's how we can make estimates about the mean values, or about the relative difference between those mean values. Right, so basically what we do is we just, so in summary, if we want to summarize that entire first part of this lecture 11, when we have paired experiments, we basically, in this case, we had 20 paired experiments, right? So 10 total pairs of experiments. We don't treat it as 20 independent experiments. We just look at the paired differences, the difference between the individual pairs, and we treat that list of, in this case, 10 differences as the sample that we're going to do our statistics on. Okay. So, but it's not always the case that we have paired experiments. We may have, to bring it back to the cab example, maybe we're trying to compare gas A and gas B, but we cannot run the same drivers and the same cabs on consecutive days, right, for practical reasons. Or, so let's say we just can't do that, right? It's not always the case that we can. But we can still use what we've learned to make an estimate of differences, right? We're not totally out of luck for comparing gas A and gas B. We can still make some estimate, and that's what this next piece is, right? So it's about comparing two means for small samples when we don't have paired experiments, okay? So I have a slightly different example. Well, that of we have two car models that are being crash tested to determine cost of repairs. The costs are summarized below, right? So we have the costs written out here in these arrays, along with sample means and standard deviations, which are computed from those arrays. Let's say that manufacturer 2 is claiming that their model has lower repair costs than manufacturer 1, right? So this might be of importance to a insurance company or something. So we're going to compute, our approach here is going to be a little bit different. So we're going to look at, we're basically going to focus just on the 95% confidence interval on the difference between the means. And we're going to look at the 95% confidence interval on the difference between the means. And we're going to see if that 95% confidence interval encompasses 0. And that'll tell us whether or not we expect that there is a difference between those two. So we're calculating 95% confidence interval on the data as the sample mean of 1 minus the sample mean of 2, plus or minus this uncertainty. And what our task then basically, as far as equation 2 is concerned, is figuring out how we estimate the standard error when we have a set of experiments that were not conducted in this pairwise fashion. So what is this SE? And then how do we construct this T statistic? All right, so that's what we're going to look at here. Now, in this lecture, we have two cases of paired means. And there are two cases of comparing two samples. And now for the second case, where we have two different sets of experiments, there are again two cases. So two things that we have to consider. So we're going to look at two approaches. Our first approach is going to assume that the variances of the two samples are not equal to one another. So if we have two sets of experiments run, in this case, we have two sets of crash repair data. We're going to start by assuming that the variances in these sets of data are not equal to each other. Right? So this is kind of the most general case. Like they were run entirely different sets of experiments or entirely different types of equipment. These are entirely different types of crashes or whatever. And so we're not going to make any assumptions about the variances between the data. The second approach we'll see is assuming that the variances are roughly equal, and that's going to allow us to pool the data and get a better estimate of what the uncertainty is. So we're going to start with this case of variance is not equal. This block of code, all it's doing is reading in the cost data and computing our statistics of mean and standard deviation on both of those sets of data. Okay, so that's what's computed down here. The mean for sample 1, mean for sample 2, standard deviations for sample 1 and sample 2. Okay. Sample sizes are small, so we're going to use the t-distribution. Right, so we don't have that much data. We're using t-distribution. We said that this is really only justified if the sample is approximately normal. Well, we're going to add the caveat here that also the sample, in order to use this kind of analysis, those two samples have to be independent from one another. Right, so they're not collected pairwise. These samples are independent. This is what our histogram looks like, though, for, let's say, repair cost 1. It's actually just pretty flat. There is slightly more frequency of results in the middle than there is towards the tails, but we have a very small sample size. And this is often the case. When you have very small sample size, your histogram, it's hard to say if your histogram is really, truly normal. We're going to proceed as if it is anyway, because, well, and one reason why we were going to proceed anyway is, I guess there is slightly higher frequency in the middle. If we made our bins a little bit bigger, we would see a bigger peak in the center. But another reason is a consequence of, we talked about the central limit theorem. So we generally expect many processes to be normally distributed, because if we add together a lot of random influences, what we end up with is a normal distribution. So we often start by assuming normal distribution, even if it's not strictly justified by the data, because we expect that many processes are normally distributed. So in this case, it would be okay to do this. You would state the assumption that we're assuming the underlying distributions are normal, but you might add the caveat that if you come back later and you realize that they're not normally distributed, then this would be invalid. But we're going to start with normal distribution. This is what our, I mean, it's actually a little bit worse. This is what our distribution looks like for repair cost 2, right? But again, the sample size is so small, it's really hard to draw a conclusion about whether it is truly normally distributed. But we'll proceed anyway, knowing that by central limit theorem, many processes are in fact normally distributed. And so now in that equation 2, I said we had to estimate 2 things, right? We have to estimate the value of the t-statistic to use, and we have to estimate the standard error for this comparison between these 2 different samples. And so the way we estimate that standard error is shown here. So it's the square root of standard deviation 1 squared over n1 plus standard deviation 2 squared over n2. Okay. So we're just more or less adding the variances and taking the square root. Okay. Adding the variances normalized by n and taking the square root. For the number of degrees of freedom, it's a little bit more complicated, but this is the expression that we use to figure out the number of degrees of freedom that are appropriate for using with the t-statistic. Note that it's not just number of measurements minus 1 or number of measurements minus 2, right? We're using an expression here. We use this expression here to figure out the number of degrees of freedom for use with the t-statistic. And that means that our number of degrees of freedom now is not going to be necessarily an integer. Okay, but that's fine. We can still compute the t distribution is still defined even if our number of degrees of freedom is not an integer. And so so we'll use this expression in equation 4 to find the number of degrees of freedom. In this case, that's computed. So the standard error is computed up here in this block of code as $161. And the degrees of freedom in this case ends up as 7.43. Okay, so again, not an integer number of degrees of freedom. We can use that. We can still use that in our t-statistic. Our t-distribution is still defined for that non-integer number of degrees of freedom. And so now that we have let's see. So we know the number of degrees of freedom to use to find the t distribution. We now have to define a significance level. So we're going to use alpha of 0.05. So now we can find the t statistic that we're going to use for our uncertainty, for our 95% confidence interval. I'm just going to scroll up to equation 2. So I said at the beginning of this example that when we're comparing these means, we have to estimate the mean of sample 1 and the mean of sample 2, right? That we can do using the same expressions that we've been using since lecture 1. And now to find the uncertainty, we need to find this t statistic and the standard error. And that was really where the challenge lie here, right? And so for the t statistic, remember the t distribution is parameterized by degrees of freedom. In this case, we found the degrees of freedom to be 7.43, right? So we choose an alpha level, we choose a significance level, and we can compute this t statistic from that. And then the standard error, we saw we're going to find by combining the variances of the two samples. And so we estimated what the standard error is for the comparison between these two means. And so now with those values, we can create a 95% confidence interval on the mean. In this case, the mean was the mean expected difference between the two samples was our sample 1 minus sample 2, the mean of sample 1 minus mean of sample 2, and that was 240. And so it looked like maybe sample 1 was in fact a little bit more expensive than sample 2, but we wanted to evaluate that. But when we compute the uncertainty in that, our 95% confidence interval on that, we get a value, our margin of error of 376 or 377. And so our 95% confidence interval on the mean goes from negative to positive. And so we would then conclude that because this 95% confidence interval includes 0, that manufacturer 2 has not shown a significant reduction in repair costs, right? So there's not significant evidence that manufacturer 2 is cheaper to repair than manufacturer 1. Does that make sense? Okay. Yeah.
So on the third example, we did any sample size.
Mm-hmm. That's where the that's why we have to use that formula to find the number of degrees of freedom. Yeah. So look at the number of degrees of freedom. The number of degrees of freedom in this case is greater than is less than 30. Yeah. I mean, and I guess the first hint should be that the numbers are so small that we should use a t distribution. I guess, and another way to address that is that you could always use the t distribution. And if it turns out that if the degrees of freedom were high enough, you'll get the same result as if you'd use the normal distribution to begin with. Does that make sense? So it's safer to use t. Yeah. Good question. Other questions? Okay, so we're going to look at an example for the second case of the variances being roughly equal. The procedure is very similar. So again, we have this equation 5. We're just going to have different formulas that we use to find the relevant parameters, right? So again, we're trying to evaluate the 95% confidence interval on our mean, on our difference in means. And again, we have to compute the t statistic and the standard error. We're just going to be combining the data a little bit differently in order to estimate in order to estimate the t statistic. So the first thing is here to find the standard error. If we can assume that the variances are roughly the same, then our standard error formula is actually the same as it was previously. It's just that now because S1 is equal to S2, or we're going to assume that S1 is approximately equal to S2, then it pulls out and it becomes, we wrote it as SP for the pooled sample standard deviation. So it's that pooled sample standard deviation times square root of 1 over n1 plus 1 over n2. And the degrees of freedom that we're going to use with the t distribution is now, so one of the reasons to do this is that it's just a lot simpler, right? So our degrees of freedom here is n1 plus n2 minus 2. So it's much simpler. We don't have to use that formula for degrees of freedom, but to find the pooled estimator for the sample variance, we'll use this expression here to combine the variances from experiment 1 and experiment 2, or in this case, manufacturer 1, manufacturer 2. So in this case, our pooled estimator, right? And remember, we're taking the square root of this in order to find the standard deviation. So what we end up with is 264. And now we run through the same process of using the, so from that we can find the standard error of the difference between the means. We have our degrees of freedom is n1 plus n2 minus 2. So simpler to calculate than that formula that we had for unequal variance. In this case, we end up with degrees of freedom of 10. And we then compute, again, 95% confidence interval on the mean. We do that here at an alpha level of 0.05. And we end up, again, with a 95% confidence interval that straddles 0. And so we do not have good evidence that manufacturer 1 and manufacturer 2 have different costs. So we would reject the claim. So this approach, assuming that the variances are equal, is a little bit easier. You end up with an integer number for degrees of freedom. All the formulas are a little bit easier to compute. So it's a little bit more convenient than assuming that the variances are unequal. A rule of thumb, in this case, if we were to scroll back up, I don't want to give you a headache, I guess, but if we were to scroll back up, we'd see that our sample standard deviations were not the same for manufacturer 1 and manufacturer 2. They were not identical. And they will pretty much never be actually identical, right? So a rule of thumb for using this approach is that let's see, so we would use the case 1 approach, the unequal variance approach, if one variance is at least 4 times larger than the other. So there's actually a pretty big margin over which the second approach, assuming that the variances are equal, is actually okay. So in this case, here we're calculating the variances here, and we see variance 1 is 8.9 times 10 to the 4, variance 2 is 5.7 times 10 to the 4. And so these two things are close enough that we can use the pooled variance method, which is just a little bit easier. Okay. All right, so I do want to talk about the quiz, and it is getting long on the last lecture before fall break. I want to point out though that there is another example from about how to use this with unpaired estimates that's given in lecture note 11. I want to point this out to you. So just take a look at this as you're reviewing your notes and as you're preparing for the homework to maybe solidify some of the things that we just talked about. Okay. But that'll walk you through, again, data from an example that we looked at in a previous lecture. Yeah, so please take a look at that. Also in these notes is a table on the different formulas that we have discussed so far for hypothesis testing. Okay, so, and this covers everything from single sample to paired samples or independent samples. Okay, and this basically is a summary of the equations that we had previously. So I encourage you to take a look at this. So we can see that for a single sample, it tells us basically what expressions to use, under what conditions we can assume we can use the normal distribution to compute the relevant statistics and probabilities or p-values, under what conditions we would use the t-statistic. The expressions that we use when we have paired samples, the expressions that we use when we have variances unequal, variances that are unequal or equal. Anyway, it's all given here. So I refer you to that as well, but these are the expressions that we've already discussed in lecture. And so we won't go through each item in the table right now. All right, yeah, and there's more. um, any questions on this before we move on to talking about the quiz? Maybe breaking for the day and then talking about the quiz. All right. So so at this point we'll take a break, or very brief break. Let anybody who doesn't want to talk about the quiz get out of here. For those of you leaving, have a great fall break. For everyone else, we'll pick up in just a minute.